With agents becoming more powerful by the day, do you even need a vector database? On episode 79 of Tool Use, we're joined by Arjun Patel. He's the Senior Developer Advocate at Pinecone, which is a vector database for AI applications. And we're going to discuss what use cases are best suited for vector databases, strategies to improve the results from your vector database, and discuss the full range from low-level details up to no-code implementation. So please enjoy this conversation with Arjun Patel.
So a vector database is a specialized data store that allows you to quickly index and query over information called vectors. Vectors can be described many different ways, but for our purposes, we can think of them as meaningful lists of numbers. And it turns out that you can encode things that are unstructured, like images, text, audio, video, sometimes even tabular or data or PDFs, into these vectors that correspond to meaning, and you can search over those vectors really quickly by using other ones. So the trick is, if you have hundreds of thousands of these vectors, millions, tens of millions, how can you do that quickly and at scale? That's what a vector database is for.
And could you give some concrete examples? What gets unlocked when we use a vector database? What is possible that wasn't possible prior?
Yeah, so any operation that requires searching over unstructured data at scale becomes possible with a vector database, provided that you can convert those things into vectors. So, for example, if you wanted to search across hundreds of thousands of images with other images to find the most similar ones, that operation is possible with the vector database and an embedding model. But let's say your embedding model also handles text input at the same time. Now you've unlocked the ability to do a sort of multimodal search where you can pass in text queries and get back images really quickly and at scale. And because the vector database has this nice property of being able to index this data very efficiently, the response times you get are going to be very, very quick, like under seconds, under milliseconds, right? So you're able to do these types of fast operations much more quickly than you would if you did a brute force search.
And just specifically around Pinecone, I've heard about PG Vector, and I think even SQLite has embeddings. What are the ranges in a vector database? Like what makes something premier versus something that's more entry level?
Absolutely. So Pinecone's a great option for anybody who's trying to do really high throughput operations or really high scale, but it's also wonderful for the starting developer, right? All you have to do with Pinecone, we manage everything for you. So you can just interact with us through the APIs. Nice thing about Pinecone is that it's very specialized in doing this type of vector search. So you could use other services that offer vector search capabilities, but if you're really wanting something that's performant and fast and focused on being able to return these items quickly, you want to reach for Pinecone. And that's where we specialize and work well at.
Is there any prep work or things like that people need to do before they go to a vector database? Do they need to structure their data a certain way or prepare to query the database differently? What's the prerequisites for this?
Absolutely. So traditionally, and a lot of this will be in the context of text data, because when you start thinking about other modalities, things get really hairy really quickly. But for text data, the thing that you usually need to do is turn it into vectors before they can get indexed into a vector database. With Pinecone, we have our own embedding models you can use through something we call Pinecone inference. So you can interact with the database entirely in text. But the second order issue becomes, how much text are you allowed to represent in a fixed size vector? And how can you search across those text vectors in order to get the best, most appropriate response? So most people have to do something called chunking, which means you take your input text and you break it up into literal chunks that are big enough to fit in size the context window of the embedding model that you're using. That's usually the extent of the pre-processing you have to do for a simple chunk-based search. So you can imagine if we had a bunch of sentences from the titles of product reviews that we were embedding inside a database, and you wanted to do some sort of similarity search where you're looking for certain product qualities that satisfy some conditions. You could pass in that query, embed all the titles of all the product reviews, and have the most similar ones return inside the vector database, and you'd be chunking at the sentence level. But if you had a Wikipedia article, you might want to chunk at the paragraph level because each paragraph encodes some sort of meaning. However, at Pinecone, we have a product called Pinecone Assistant now where you can just throw your PDFs in and it'll do the chunking for you. So there's lots of different options to use the underlying vector database, but traditionally you got to do some chunking.
I've heard different techniques around chunking strategies. We had Kirk Marple on a while ago, and he talked about wanting your chunks to have a little bit of overlap with each other just to make sure you're not doing a hard stop to kind of bucket the context. Do you have any insights there? Even though I know Pinecone Assistant could help with that, just for people to get an understanding, what should they think about when they do their chunking?
Yeah, so this is one of the most frequent questions we get asked, to the point where like we have an article on our website that's like one of the most viewed articles on our website that's about chunking strategies. And the hard truth is that it really depends on the type of application that you're building and the type of search that you want to benefit from. But there are some heuristics that are pretty helpful. What I normally tell people is to try the simplest chunking strategy that you can implement on whatever data that you're working on, and hit your data set with some queries and just see how it feels querying the data and getting the responses back. And as soon as you start looking at how your data looks like once you've applied some sort of chunking strategy, you will quickly start to see some of the holes and issues. For example, one of the common techniques that people implement to fix a okay chunking strategy is something called chunk expansion. So if you have a bunch of chunks in a document, let's go back to our Wikipedia example, you have a bunch of paragraphs that you're chunking. Sometimes the paragraph that you've embedded might not contain the entirety of the argument that you're trying to retrieve given some query. So it might just be a helpful heuristic for you to look at where that paragraph is relative to the rest of the document, and then pull out the additional chunks above and below that chunk in order to return an entire kind of document there. Pinecone Assistant does that. You could also do that yourself by including chunk numbers and then just retrieving the -1 chunk and the +1 chunk. And that can kind of remediate any sort of like not optimal chunking strategy. So I would say like start at like a meaningful unit of information that you feel like is relevant for you. So for Wikipedia articles, like paragraphs are pretty good. Maybe you have a really structured like textbook and you're like, okay, these chapters and subchapters should be like really the minimum amount of information we need to look at. Or sometimes people do entire pages if you're dealing with like multimodal PDFs and like, all right, each page will be my chunk. Trying something is better than nothing, and trying to understand how far you can go with a simple method is better than applying something really complicated, spending a lot of time, and then not getting good results.
Yeah, and when you mentioned potentially doing a full page, is there an upper bound to how much you can put in? Does it depend on the vector size?
So that's a really good question. It's really dependent on the type of embedding model that you're using, what its context window is. But like with chunking, there's some heuristics that you can follow that make it easy to kind of do. So it used to be the case that people would say that you could fill up the entirety of the chunking window, the context window of an embedding model. So if an embedding model's like context windows like 1024 tokens or 2048, you could just count the number, you should tokenize your text, fill up to that amount, and just throw it inside the embedding model. But there's some anecdotal evidence that says that if you do this for embedding models that have particularly large context windows, so greater than 2048, so on and so forth, you might start washing out or averaging over the information that exists in that chunk, and therefore it no longer becomes relevant to any query than any other chunk would be. So in that regime, you probably want to only fill up like half to maybe 2/3 of a context window and kind of go from there. So that's kind of what I would say. And it also depends on the complexity of your text. So if your text is very information dense, then you want to have smaller chunks that allow you to retrieve that information kind of independently of one another. But if your text is not information dense, then it's okay to kind of pack more information in there. But yeah, it depends on your embedding model. It depends on your depends on the amount of information you're passing. But the vibes kind of tell me that like as embedding models get really good at getting more and more information in, that doesn't necessarily scale the same way as how that information is getting represented. Similar to how if you have a context window for a model that's like 200K, 1 million tokens, even if you jam all that up, you're not going to get that great of a response out.
Yeah, we very traditionally keep it under 50%, if not lower, just to make sure we get the better results, especially with coding models.
Right.
Just on the note of embedding models, I'm admittedly not very well versed in it. When you talk about embedding models being better than others, is better just in terms of having, because okay, backing up a bit. My idea is it takes a certain amount of information and puts into a number of dimensions with a value for each dimension. When an embedding model is better than others, does it just mean that number, like the vector has more precision? Does it just have a better representation of the information you give it? Like what makes one embedding model better than another?
Oh man, this is like one of my favorite topics, and this
Nice.
is like something that I've thought a lot about for many years. So one courses I took in college on like AI/machine learning, because there weren't that many offered at the time I was there. was on vector embedding. So this was like the first kind of thing that I was introduced to. And all of the techniques there are going to sound almost alien to like anybody who's working with vector embeddings now, because we're talking about techniques that work much differently than the embedding models that do now. For example, we could be talking about bag of word like techniques, which rely on the frequency of how often a word occurs in a text and apply some sort of weighting algorithm to that frequency in order to determine its importance or meaning. Whereas now we have like this completely unsupervised method that just like produces a list of numbers and it's not necessarily interpretable inside those numbers. So I'm going to try to give you like a brief overview of like how these things are supposed to work. And then we can talk about like what makes different things better and more interesting. So at first, when you had embedding models, you'd had very simple heuristics that didn't deal so much with the relationship between the words in a given text. So if you think about searching on Google before like, I don't know, 2018, 2017, 2016, like before they switched to a transformer kind of model, when you search something, you type in as many keywords as you can before you get a text that kind of maps with that keyword, because you're basically just trying to hit all of those words that are inside the thing that you're relevant, thing that you're interested in looking for. But the trick is that these words actually have meaning associated with them, and the meaning of the words depend on how they occur inside of a sentence. So you can think about like homophones, like I went to the park or I'm going to park. Like those mean different things in different contexts because of the way that they kind of relate to one another. So there's this idea called the distributional hypothesis, which claims that words can you can kind of understand what words mean based on how they cluster around the words that are around them. So if you look at a word and you look at the words next to them, so there's something about the words that co-locate with that center word that can give you information about what that word means. And it turns out that if you train a model to say, hey, here's the first 4 words in a sentence, can you tell me the 5th word? Or here's a sentence that has 10 words, I'm going to throw away 3 or 4 of them randomly, and I want you to guess what words should kind of go in there. If you train a model with that objective, it turns out that you can learn a lot about the meaning of words from that task. So if you think of like Mad Libs, or you can think of just like charades, right? Just like guessing words and trying to complete those things. So we figured out how to train models that can follow that sort of learning objective. And the representations that these models learned in order to achieve that objective turned out to be very good at representing the underlying concept. So this is like the second wave of like embedding models, being able to represent what these words kind of mean, right? And so the differentiation here is the loss function. So how is the model learning this information to generate this representation? Is it getting better at guessing the words that are there? And then also the data that's being trained on. So the Wikipedia, the internet, whatever corpuses you're going on are going to affect like this distribution of words that are kind of occurring, right? And it turns out that you could abandon this idea of working only in English. You could train a model that predicts on a sub-word level or token level, literally looking at like how often certain characters are co-occurring, and train on tons and tons of languages and learn something fundamental about how tokens co-occur, which inform the meaning of those words. So you start getting surprising research results like, oh, we were able to kind of train on the entire corpus of multilingual data, and now we have a way of kind of searching across languages, even though we haven't necessarily cracked a deterministic way of translating across those languages, right? There's something inherent about how these words are coexisting that informs information there. So going down to this token level, allowed us to kind of capture more of this generalized information, right? The last kind of way you can get more power out of embedding models or build embedding models that are cleverer is going to be your data set distribution. So the previous thing I described was like loss functions and then like clever ways of pre-processing the data, looking at the sub-token level. And the last thing is data set distribution. So this is where you get specialized embedding models from. So if you want to, say, do legal search really, really well, and it matters to you how to represent this domain-specific terminology, then you probably need an embedding model that has been fine-tuned on that data in order to really understand what's going on there. Because for the same reason that words mean different things in different contexts, there are certain words that have extremely powerful meanings in specific contexts that these generalized embedding models will never have access to. So if you're working at a large organization, you have tons of internal data, maybe there's a concept or an idea that you refer to that means something way different than it would out on the internet or out in the wild. So changing the data distribution of how these embedding models are trained on are going to really affect their ability to retrieve this information. And there's also this idea of fine-tuning for information retrieval. So not only do we so before I described tasks of like, oh, guessing words, like, oh, like we can like complete a sentence, or we can fill in like what's called masked sentences. Like that's cute, right? But we care about actually finding information. So why don't we train on finding information? So you'll have data sets that are like, here's the input query or real question someone asked, and here's like all the documents that are actually relevant to that input query. Can we produce a model that takes that input query, creates an embedding, embeds these documents, creates another embedding, such that the relevant documents cluster closer in vector space than the unrelevant ones? So now you're actually learning the signal that is important for the task that we're describing, which is semantic search. And that's kind of like this latter class of embedding models that are getting really good at representing user questions and kind of returning things back. So that was a little long-winded, but that's kind of like why you have to care about embedding models and what they kind of do. And the ones that we host have these properties of like, not only are they good at generalizing, not only are they good at blah, 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 they're also really good at doing information retrieval, which is why we've kind of selected them to be on our platform.
Okay, very cool. Appreciate that explanation. I'm going to take a swing at just explain my mental model of what semantic similarity is, and you just tell me how off I am. Because
Sure,
I
yeah.
had trouble just like picturing things in, 10, 24 dimensions. I just can't really comprehend that. But when someone broke it down and just brought down to two basic dimensions, two arbitrary points in space, the semantic similarity is kind of like the angle between them. And if you wanted to have something like with a smaller angle, it's more similar, and a bigger angle is less similar. So that's why semantic similarity kind of gauges like what your threshold is for difference. Is that okay? Am I kind of close?
Right. That is one measure of semantic similarity. And again, it depends on the embedding model and like what distribution of angles your embedding model produces, but that's like a detail, right? The overall idea is the closer in angle you are to this input vector or query vector, the more semantically similar and relevant you could be to whatever question that you're asking. And it's crazy, like when you look at some of these like word plots that some of these embedding models produce, you'll get things that make a lot of sense. Like you'll have like the embedding for dog, and it'll be next to like things that dogs do or things that dogs like, and you'll have the embedding for cat, and it'll be next to the things that cats do or cats like. But hot dog won't be near any of those things because it means a completely different thing. And you're sitting there like, how does this work? Like, how does this make any sense? And it just turns out it just does. Like we can just learn information from how these words are used in context. It's pretty wild. But that explanation is more or less correct. Yeah.
But in terms of trying to fine tune a system, so I have my vector database up, I have a few queries, and I'm not totally in love with the results I'm getting. Is semantic similarity the one knob that I turn, or what else would I try to adjust to improve the quality of my results?
Right. So having a good embedding model is one piece of the puzzle of building a performant semantic search system. And semantic search is like a good layer of abstraction to kind of talk about all kinds of applications you can build with Pinecone or with other vector databases. So we're talking about recommendation systems. We're talking about like RAG chatbots. All that stuff is basically doing some sort of search under the hood. So this is kind of like one layer, right? And the embedding model will control how much fidelity you can initially get with like your query and like all of your documents that are being represented. But there's still other engineering decisions or even other models that you can kind of apply to the system in order to improve the quality of your results, but beyond like what the embedding model is giving you. It's kind of like one thing you can do. So a common recommendation we give at Pinecone is to apply a re-ranker to your results. So we talked about embedding models, which kind of like allow you to represent queries and documents in vector space with respect to their meaning using vectors. Re-rankers do that kind of, but instead of outputting an embedding, they output a score. So there's two trade-offs to think about with these types of models. So ideally, what happens is you have a query, you embed that query, and you have a bunch of documents, you embed those documents. But when you embed those things, you're trying to extract the meaning or the information inside the query and each document independently. They don't know about one another. And that's nice because it means you can embed all of your documents independently of embedding your query. So you can pre-index your vector database without having to rebuild your index every single time as you get a new query in, if you had to think about them in context. So that makes that type of system very performant. And this is a property of like any vector database. And the compromise, though, is that there are situations in which you'd want to adjust the influence the idea of relevance or similarity has based on the query and the document at the same time. So what a re-ranker does is that it inputs a query and a document at the same time with context of one another, and it outputs a score between 0 and 1 usually. And that score correlates to not only the semantic similarity, but the relevance of the document to the query. So it's possible to have documents that are semantically similar, but aren't relevant. They could be about things that are close in meaning to the thing that you're trying to ask, but they're not the thing that you're actually looking for. So we consider this as sort of refining step after doing an initial semantic search. So you do a search, you have a million documents, you reduce it down to like 100 or 200 documents, and then you apply a re-ranker and you reduce it down even further to the top like 10 or 15 documents, and you return that back. So that allows you to increase the quality of the already good results to something even better without having to re-index everything. So that's like one thing you can do. And there's tons of other tools in the toolbox to make search better, but that's like one thing we recommend.
Okay, and just so I'm making sure I understand the
Yeah.
re-ranker concept, it won't impact the embeddings in any way. It's just like a filter after a query returns a number of chunks or number of embeddings, I should say.
It is a scoring algorithm. So you could say it filters for like the most relevant documents, but mechanically it's rescoring everything, giving it a new score, and then you order by that score and just return everything past the cutoff. That's why I like to refer to it as refinement, because you get like 100 documents and then you're saying, okay, I want to further refine the quality of these 100 documents in the context of this query. So then you reorder those documents and then you just take the top 15 most relevant ones and return that back to the user.
Right. And are re-rankers the type of thing that can be fine-tuned? Based people, they see the performance like, I actually wanted number 12 or 13. Let's readjust it so that gets higher ranking.
You could. There are limits to how effective fine-tuning is for like the developer. It depends on how much data you already have and if your data are labeled, right? It's not easy to fine-tune. Usually when you want to fine-tune something like information retrieval or a re-ranker, you need data sets that are like, here's the query and here are the relevant documents. And most people don't have that because they don't have a system in production yet, or they don't have it in the format that they actually need. So you might have like data about, I don't know, things that users are clicking on, but you might not know if that's actually relevant to what they need. It might just be a good heuristic. So it is possible to fine-tune any of these models. It just depends on how specialized your domain is and whether you have the data to support that sort of operation.
And is there anything such as metadata, or I'm thinking like a tagging system to put on embeddings to kind of highlight them? Maybe it's from like a certain book or a certain chapter, something, so you can, instead of going across everything, be like, I definitely want from this area, reduce the list that way.
Yeah, so this is another common thing that people do with vector databases and on Pinecone. So we have two main systems of letting you, and this is where like the engineering concerns of like building a search engine really come into play. So you can imagine that if you were some large like organization, or maybe you were just like a developer that's really good at like getting data into whatever system that you're kind of making, building your own Wikipedia or whatever, right? Indexing all of your notes. You could have like 1 million documents or 100 million documents or something insane, right? And even if we have performant indexing algorithms, you might not want to do a search that like does something to all of those operations, right? You want to reduce the scope of the search somewhat if you have some information at the beginning. And there's two ways to do this with Pinecone. One is metadata filtering, which is what you described. So every time you upsert a vector, which is our terminology for putting data into your vector database, you can attach metadata to that vector. And you can also filter by that before you're doing the vector search. So that means, hey, everything that satisfies this, pull that and then do the vector search over that information. So you're still getting the benefits of a really performant vector search, but you're not scanning like the entirety of your index because you don't need to, because you already specified the filter in advance. So you could do this with content. You could do it with languages if you had multiple languages in a vector database, or sections of a document, anything. And the second layer of abstraction, which is more strict, is namespaces. Excuse me. So namespaces are like partitions on your index that allow you to enable a multi-tenant architecture for your users. So let's say you have a ton of users and you don't want users to query each other's data, but you want them all to live on the same index so that you can benefit from Pinecone's like auto scaling infrastructure. We scale independently of queries and writes, and you don't necessarily want everyone to have like their own server or whatever. You kind of want them to all live on the same infrastructure, so their latency is like quite low. Namespaces let you specify that level of partition in your database so that you're just querying inside there. So each user could have their own namespace, and then you're just querying inside their partition of the vector database.
Are there any other pre-filters or things that people should consider to help making sure that the results they retrieve are accurate?
So metadata filtering is the big one. And then there's sort of like, and of course, metadata filtering can be used for content type, any sort of operation that allows you to, if you have this information in advance, what data you're kind of putting into Pinecone and how you can sort of tag it. But another thing you could do is have separate indexes and then use some sort of routing mechanism in order to push people toward one index or another. So for example, you can embed data in different ways, which allow for different sorts of benefits. Like you can embed information with a dense embedding model, which kind of exposes more semantic, meaningful concepts out of your data. Or you can use a keyword or sparse embedding model, which really focuses on the words that are being used and their meanings inside that context. And there might be situations in which you want to route a user toward one type of search method versus the other. And that way you're not hitting the entirety of the index at the same time, but you're just hitting the specific kind of search method that they need. That's something that somebody could implement like on top of Pinecone to route queries. We call that query routing. That's another way of kind of like filtering results down. Or if you think you have an agent and it has access to many different databases, you don't want it to hit every single database on every single query. You want it to know about what information is inside each database and then only use the data from the relevant databases. It kind of meta there, right? You're doing a relevant database search before you do a relevant data search. And that can reduce your search space as well. So beyond that, it's more engineering concerns before you get to Pinecone, but metadata filtering is the really big one.
How well does a hybrid architecture or general advice you have if someone wants to use SQL for a portion of the information and vector for another portion? How should they think about dividing it? How should they orchestrate it? Is it just simply having two simultaneous ones, or what have you seen there?
Yeah, so this is a problem that a lot of like developers run into, especially when they already have one database and they want to kind of figure out another. So sometimes people will want to do like tabular structured operations on their vector data, or they'll have their tabular structured operations, but they want to do a vector search, and they're like, well, how do I, like, what are these heuristics I need to think about, and which data store is best for what? So my advice would be is to think about the type of search that you want to implement and what field or fields of your data that you're already collecting are going to be important for that type of search. That is the information that you want to put inside Pinecone, because you can only embed like one kind of concept in each of the indexes that you're kind of working with. So an example would be like, let's say you have product reviews and you have all this information about the products, like what it is, how much it costs, so on and so forth. That's like kind of your structured data. And then you have the product reviews, which map back to the products. And the product reviews are completely unstructured. People can write like whatever they want. So you might want to store information in Pinecone being the product reviews. Maybe you have another index for just the titles, or you put the titles and the reviews in the same index and then use metadata filters to identify one from the other, whatever you want to do. And you have a unique ID that maps back to your structured database if you need to pull this other information that's relevant. And that way you're concentrating this like very specific kind of data that requires this vector search inside Pinecone, which is what Pinecone's really good for. And then whenever you need to run your structured queries, you can do that with your other databases. It's really tempting for developers to kind of like flatten their existing databases and then put that all inside Pinecone and then try to do searches over that. So like you can imagine if we had a product description and all these attributes and all this stuff, you could put it into one big text chunk and then embed that whole thing. That ends up doing this sort of averaging of information that we talked about earlier, where there's like too much stuff in each chunk. And that's not what you want to do. You want to figure out the exact thing you want to help people find and build the search for that thing.
Okay, so for a concrete example, in my world, at Box One Ventures, if I have information on a company, the location, the head count, the founding year, all of that still sits in SQL because it's very direct, easy to query. But a description of what the company does, a description of the science that led to their discovery and whatnot, things where people would say, hey, like I need information on certain types of therapeutic companies. That would be more appropriate for a Pinecone or vector database because it's not going to be as binary, give me this one field.
Exactly. And maybe there are certain operations that you do along with that that are just useful to have inside Pinecone as metadata. So maybe the industry, you've already pulled this information out from the company. So it just makes sense to be able to segment your searches inside Pinecone by industry. So if you care about medical applications and then you're searching inside the subsection of medical companies about the specific innovation that they're exposing, you can see how that would work. But what's interesting about this conversation is that it reveals a trend that has changed over the past 5 or 6 years, and something that I've seen a lot of. Because when I started developing as a data scientist, like the initial answer would have been to build models to kind of pull information out of these structured descriptions in order to populate the structured database and then do queries over those, right? Like build a model that can predict the industry of a company or try to extract like the thing that they're building, all that sort of stuff. Now we have these powerful ways of kind of abstracting that search out so we don't have to do this upfront engineering work, right? It's kind of amazing. Like we can offload this type of querying to this agent or the representation of the information to this embedding model so that we can find this information faster. That's the key value there.
And one thing that I've been exploring with is just having let's just say my Obsidian vault, so a collection of markdown files, let Claude Code loose on it, it'll figure out what it needs, and it'll bring back that information to a natural language query, similar to how a vector database would, without all the steps in the middle. What are the pros and cons to that approach? Because like you mentioned, the speed is very fast with vector database, and having Claude go through a bunch of things is very slow. But what else should people consider of those two approaches?
Yeah, so this is like very interesting argument, right? And I think that this depends. Obviously, there's a lot of like qualifiers on the exact type of search that you're doing, what your tolerance is for the relevance of the results, how long you're willing to wait. And I think it's really tempting for people to draw the conclusion that as long as I start a task and then have the result of the task come back, that's okay. That's like kind of good enough. And there are a lot of situations where that's completely fine, right? Like maybe Mike, you don't need like the most low latent search for your Obsidian docs because you're gonna ask a lot of questions, you're gonna walk away, and then you'll come back and you'll kind of have the answer, and that's like okay, right? That's completely fine. But maybe you're realizing that hey, you know what? Claude is doing a lot of queries and a lot of text searches, and a lot of tokens are kind of being used up. Maybe this is a problem. Maybe I need a way to kind of quickly identify which documents are relevant. And then once I do that, Claude can do grep search inside there. So it doesn't necessarily have to be mutually exclusive at all. Of course, there are engineering concerns like like making sure you upsert all of your data and keeping that in sync. But we find that semantic search can be a lot more flexible than just doing keyword searches repeatedly. And of course, you're going to save a lot of tokens if you're getting the results back the first few times. So yeah, that's kind of like what I would say. It's completely fine to just use what you think is helpful. But I think if you look closely, especially at how Claude is doing searches, it is a brute force method. It doesn't know about what data you have. So it's just trying to find things as you could. And it's kind of fast at it, so it can do it quickly. But you have to think about the consequences of doing so many searches. You're going to fill up your context window really quickly. And at some point, you have to decide if that's worth it over a really large database.
Yeah, and similar to like you were mentioning earlier, if it's just grepping through a file for dog and there's something about, a leash, it's not necessarily going to come up with it, so it might miss it completely. Just on the note of concrete examples, having worked at Pinecone, what are some cool, unique use cases you've seen where people might not traditionally think a vector database is the right solution, but it turned out to be great for them?
Yeah, so I think that a lot of people think about Pinecone and vector databases for retrieval augmented generation, which is like, hey, you have a chatbot, you upload some documents, and then it searches over the stuff and you get answers back. And I think that's like fine, but there are a lot of really interesting like industry specific applications that are particularly powerful that rely more on this idea of being able to do semantic search really quickly rather than like, being able to generate like the appropriate or correct response. So one of, and outside of that, I think one of the interesting applications of semantic search is recommendation systems. So what people might not realize or think about is that recommendation systems are a form of search where you have an input query, which might be users' preferences or their previous shopping history or whatever might have you. And you have a bunch of information that's been embedded that can quickly be things that are relevant to them. And the ability to kind of make that sort of operation possible very quickly is super cool. And I think that building recommendation systems on top of Pinecone is like very, very underrated. I have a fun example of spinning up like kind of a quick, simple one that I can show you in a couple of minutes. Another thing that I think is really cool personally, that's kind of outside of a super funky enterprise application, is the ability to encode data that normally you wouldn't think would be easy to encode or map up. So I'm talking about like multimodal search or multilingual or cross-lingual search. One of the first things I learned at Pinecone is that there is such a thing called multilingual embedding models. And these are embedding models that have somehow figured out how to represent like hundreds of languages in the same embedding space. So if you ask a question in English, you'll get the correct responses back in other languages. And there's not a clear reason as to how this translation is actually occurring under the hood. It's just the property of how the languages are being used like across the world. So you can do crazy things like just do translation without having to actually translate because you're using an embedding model that finds the most relevant information to the given input query purely off the property of the semantic similarity search. And once I built that demo, I was like, oh, there's something very interesting going here. And that extends to any modality. So you can do text to image, image to text, video to video, audio to video. If you can represent it in the same embedding space, then you can search over it, and things get really crazy really fast.
Well, you mentioned demo, and we talked before that you have something set up with Claude Code, which is getting hotter than ever, especially with 4.6 coming out today. So would you mind giving us a little demo?
Yeah, absolutely. So a little preface. So at Pinecone, we think really hard about how people are using us in their agentic IDEs like Cursor, Claude Code, Copilot, Anti-Gravity, so on and so forth. And so we've been developing a lot of content at Pinecone to help people be successful with our products inside those environments. One of the things we developed was a plugin for Claude Code. You can find this plugin on the Claude Code official marketplace. Chances are, if you have Claude Code, it's already on, the marketplace is already installed in your session. All you have to do is hit /plugin install Pinecone, and you can start using our plugin. So I'll walk you through some demos on semantic search and assistant if we have time. It'll be super fun. Let me go ahead and share my screen and get started. So I'm inside VS Code right now, and I've fired up Claude here. I've already have our plugin installed, and I'll show you what that looks like. And I've also have claimed an API key from my Pinecone account, and I've exported it in my environment before I go here. Not going to show you that for obvious reasons, but be aware that you'll have to export your API key. You can get one for free at pinecone.io. Cool. So what I'm going to do is I'm going to find the help command from Pinecone. So I'm going to type help here, and you can see we have the / command, which explains how to use Pinecone inside Claude Code. So I'm going to go ahead and hit that. And what it's going to do is it's going to check that an API key has been set and that we can list our indexes. So we can see that we've invoked the help command. We have some features we have access to. We have a bunch of Pinecone Assistant commands. I'll go into that in a few seconds. We have access to our Pinecone MCP server, which means we can create indexes, do semantic search, list our indexes, all that sort of fancy fun stuff. Some / commands, which let us explore our data. And we have some setup instructions. So it looks like we were able to successfully list our indexes here. I'll use Control O to kind of show you what that looks like. This is an output from our MCP server, which shows us the indexes that we have access to. So it looks like we're all set up, and we can start exploring our indices. So I have some fun indices that I've set up for us to kind of look through. I have a few here. I have one that's just like a simple sentence search. I have one that indexes 50,000 Wikipedia pages of North American birds with 2 different methods. So we can kind of understand like how semantic search works in one domain and how sparse search works in another domain. And I also have a recommendation system example that kind of shows us how someone could do recommendation systems with food as kind of the domain. So what I will do is I will start with this first simple semantic search example so we can get our bearings, and then we can do the bird search one or the food one, depending on what you're interested in, Mike.
Oh, well, so we got to do bird to search for a puffin.
Okay, cool. Awesome. Hell yeah. Oh, Mike Bird, of course. Oh my gosh. How could I,
it all works out.
even not notice? So let me go ahead and query this semantic search index that I'm describing. So this is an index of English sentences that are about going to the park and parking your car. So a very simple example of semantic search is just trying to disambiguate the fact that park is being used in 2 different contexts. So I'm going to go ahead and say, okay, I want to query my semantic search index, and I want to say, where do I have to park? Right. As I'm running this / command, Claude is going to figure out what index I'm kind of working with. It's looking what parameters it needs to kind of pass in, and it's going to go ahead and do that search. This is all MCP calls that are being enabled by Claude. And now we're getting some outputs back, and we can see what's kind of going on. So I said, where do I have to park? And I got a bunch of queries that are coming back that are about parking my car, right? And this is interesting because we're not at any point doing a mapping over the query that I'm looking at and the text that's coming back. This is just the meaning of the sentences. And I can demonstrate that by asking a different kind of query. So instead of where do I have to park, I can say something like, I want to play, and I can see what sort of sentences kind of come out of that. So I can say, I want to play at the park. And the same type of operation will happen again. It's going to search the same index because it saw that I'm kind of passing in the same query again. And it'll generate a list of the things that kind of come back. So I went to the park to play tennis. I am playing in the park, so on and so forth. And we didn't get any of the other sentences that I showed you prior of like, where can I park, blah, 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 blah. So this is like a very like 101 example I like to show people to like really nail this point. At no point are we actually like looking at the words that we're using inside the documents or the query. This is all embedding models like all the way down, which is crazy to think about. So now that I've shown you that, are you ready for like this bird kind of search example?
Yeah, absolutely.
Okay, awesome. So I actually built an application that basically shows users how to index information in different ways in order to expose different properties of semantic search. So we've been talking a lot about like representing concepts and ideas, and a lot of that comes from using what's called a dense embedding model. These are embedding models that take in documents and produce embeddings based on the entirety of the meaning in the document and less so on the words that are being used. Sparse embedding models place a greater emphasis on the words that are being used rather than the entirety of the meaning of the document. But they reweight the influence of the words based on the other things that are kind of occurring inside that document. So why does this matter, right? You can imagine situations where you'd want to do a sort of keyword search, but you also want to preserve some of the meaning of the query that you're passing in order to adjust like what words kind of happen. We were doing a little bit of that prior, where I was saying, hey, I want to go play at the park. So we want to find sentences that include the word park, which is relevant for us, but we care about how the word park is being used in that context. So we still need an embedding model to inform the representation of that word and change it because of the context being shown there. So I have an example of having indexed the same data with these two different methods, and I'll show you the differences in the data based on those querying methods. So what I'm going to say is, hey, Claude, can you list my indexes that are named bird? And those are going to be my bird dense index and my bird sparse index. So I'm going to go ahead and have Claude list those indexes and show me which ones they are before we can actually query them. Okay, great. So I have a sparse bird index and a dense bird index, and I have a best match 25 one, which is just regular keyword search. We won't talk about that one here because we can't easily query that one with the way all of this is set up. So we're going to run our experiments on the sparse bird search and the dense bird search. So I have some prompts here. This one is large predatory bird that hunts small mammals at night. Okay, before I send this out, what kinds of data do you think are going to return if we were to ask this in like Wikipedia search, for example, or in a very keyword based way? Like, what do you think we're going to see like in the return information?
Sorry, like an owl type thing?
Yeah, it could be like an owl. It could be probably a paragraph about an owl describing its hunting tactics, right?
Right.
But what's interesting about this sentence is that we're never describing the name of the bird, right? We're describing the property and the idea of the bird. So my hunch is that this will probably work better with a dense search over a sparse search because we don't really care about like specific terminology or information. There's this idea of this bird that we're trying to look for. So I'm going to say, hey, Claude, I'm going to use my query / command. So I'm going to go down and hit tab and I'm going to say, hey, Claude, query this sentence in both sparse and dense indexes and return the results. And then I'll paste the sentence and we'll just compare the results together and see which one is better, one or the other. So we can see it's making a bunch of MCP calls and then it'll format both results for us. It's searching both of these things. and it's inputting that query that we care about. And now it's honking. That's so
So
pretty
fitting.
on point there. And then we'll just see what kind of pops up here. Okay, awesome. So let's look at the search results here. So for the first result, we did using Pinecone sparse. We got the Costa Rican pygmy owl, and the details that we got is that it forages day and night and hunts from a low perch. The diet includes birds, small mammals, vertebrates, and arthropods. And then with the dense results, we got something that specifically preys on hummingbirds, which is interesting because we didn't specify hummingbirds at all, right? And it's also a bird of prey. We got the western screech owl, which is maybe kind of large, and it kind of eats these other things like mice, rats, flying squirrels, bats, so on and so forth. We're not seeing the raw information. I think Claude is helping us here by kind of cleaning up the return results that are being generated. But you can see that we're kind of extracting different ideas or properties because of what's going on here. And let me go ahead and just like show you the results. So let's look at our sparse search here. So we got the Costa Rican pygmy owl forages both day and night. So we got night in our query here, and we got night kind of returned here. It hunts from a low perch, and it takes prey. Its diet has not been defined in detail, but it's include birds, small mammals, and other vertebrates. So we have another hit here on small mammals, which is why we got this result back. Now let's look at our dense search. Let's see the first result that's coming back. It's diurnal. It's found primarily around humid forests, and it's known to prey on hummingbirds. So you can immediately see the difference in the quality of the results, right? So here we got...
Sorry, it even describes it as a small bird rather than large.
Exactly. Which is probably just something that is not as relevant, right? Like it probably got confused by this idea of like preying on hummingbirds versus being small. There's like too many attributes that we're kind of searching here. But it's still really interesting that we got a result that's like, hey, this is eating like really small hummingbirds, right? There's like something like valuable or interesting there. This second one is probably way more relevant. So these nocturnal birds wait on perches to snoop down. They catch insects in flight, not mammals, but they do eat mice, rats, flying squirrels, and bats, other birds, and they're opportunistic predators. So this result would probably be a lot more relevant than some of the other things that we got with the other model. Okay, you did say you wanted to search information about puffins. So I wonder if you wanted to take a stab at forming a query and seeing which index gives you better results here. Is there anything you want to know about puffins? And then we could kind of like go from there.
Migratory habits.
Okay. So what are some migratory habits of puffins, right? And
Nice.
Are there puffins in North America? I hope there are.
Yeah.
We
have actually different ones
cool.
on the west and the east. So.
Oh, really? Wow. Okay. We got an expert. Okay, awesome. So I'm thinking that this would probably perform better in our sparse search because we're really keying in on this terminology of migratory habits, but we might get some sentences that are relevant as well. So let's go ahead and inspect the results ourselves. So here's our sparse search. First thing we got was the Allen's hummingbird. All right, that's not what we're looking for. And it looks like we're getting migratory patterns back. So this probably over-indexed on this idea of migratory patterns and not on the actual bird that we're interested in. However, the second block that we get back has something about the Atlantic puffin, which is pretty awesome, but it's more about the characteristics of that puffin rather than the results that we were interested in. Let's go back here. Okay, great. So those are our first two kind of like sparse results, right? We got another puffin kind of section here, probably another part of the same article. And then we got tufted puffins back here. So it looks like we got information about puffins, but not necessarily about their migratory habits. So that could just be a data set issue. Like we might not have good information there. In the dense search, we got information about puffins right away, which is really cool. It looks like we have the Atlantic puffin. We got the dock horn puffin, which we didn't see in the opposite results. We got the Atlantic puffin again, but the sentence is more about like their habits that they kind of do in danger. And then we got one sentence about migratory patterns from a different bird. And then the tufted puffins, which also are not really talking about their migratory patterns. So we learned something interesting here, right? Like maybe there's something about the way we're chunking our data that's just not capturing this migratory information at the same time as it's capturing information about the animal that we're interested in. But we were able to kind of see the different results that each search method produced and maybe make actionable choices based on that. So, okay, I know that we're not supporting migratory queries that well. So maybe we'll have to think about how we want to chunk around that specific idea in general, especially if a lot of our bird search users are trying to find that sort of information. But yeah, that's kind of the idea. That's kind of how the plugin works. I have a few more things to show you, but I know we're kind of running up on time, so I don't want to take up too much of it.
Yeah, no, happy to keep going with this.
Okay, cool, awesome. So that's kind of our search demos there. There's another functionality of of our Pinecone plugin that people might be interested in if they want to do the whole retrieval augmented generation pipeline without having to build it entirely themselves. So we have a product called Pinecone Assistant, which sits on top of our Pinecone database, which is like our trusted knowledge kind of infrastructure layer. And the idea is a lot of people want to chunk their data, but they don't know how. Or a lot of people have their data in PDFs or text files or all that sort of stuff, and they just want to start asking questions over that data. So we created a way for you to instantly chat with your documents, upload them, and then get generated answers off of them, along with citations and references back to the documents that you're kind of looking at. So you don't have to build this whole pipeline yourself. You can just say, hey, here's all my documents, go put them inside Pinecone, and then let me query over that data. But we didn't stop there. We also handle the query planning and orchestration for you. So it's not just a simple semantic search over the information that you care about. We do a lot of subqueries that break down the question that you're asking. We search all of those results, we re-rank them, we present the results back to a language model like GPT or Claude, and then we generate a response for you. And then you can even see how the model generated the response based on the data that it searched over. Now, there's a lot of ways to make a Pinecone Assistant. You can make one inside of our console, but I was able to kind of create a no-code experience inside the plugin. So I can just tell Claude to make my assistant for me, upload these documents, and start chatting with it. So that's what we're going to try to do here. So I have this folder here called Assistant Documents, and I've put in a bunch of PDFs in this folder. They're all about different kinds of AI research. So one is about how people write agent.md files. If you're familiar, they kind of help control the generation of the code that you're creating. One is a recent research paper. Oops, don't want to open that inside VS Code. One is a recent research paper that discusses skill formation over people that are using code generating models that Anthropic kind of produced. And then I have research papers and articles that we wrote and research papers that we gathered relating to sparse and dense search. So I can say that my goal is, hey, I want to combine all of these sources and I want to think about how I can write like an agents.md or a skill.md file to teach developers how to do sparse or dense search. Like, here's all this information, synthesize an answer for me. So what I'm going to do is I'm going to first ask Claude to create an assistant, and I'm going to ask it to upload all of this data from this document here. So I'm going to say, hey, Claude, using the assistant skill, can you please create an assistant with I'm going to add my folder. Oops, typing is hard. Docs folder. And we'll go ahead and see what happens. So ideally, we've created a skill and a bunch of slash commands to kind of make it easy for Claude to create assistants, to chat with them, upload documents. And you can see that it found our Pinecone skill. And what this skill is going to do is that it's going to create, manage, and interact with Pinecone assistants, so on and so forth. So I'm going to go ahead and click yes. It's going to load information about what it's able to do. And now it's going to create our assistant, and it'll probably ask me for a name. Oh, it created the name for me. That's fine. We'll call it the Tool Use Podcast Docs Assistant. All right, that's cool. And now it's going to go ahead and upload the documents. So what's happening under the hood here is that inside of our plugin, we've packaged the skill / commands and a bunch of scripts that Claude can use in order to, say, upload these files to our assistant or query them. And this property is really nice because we don't want Claude to generate the code to upsert the data every single time, because that's a lot of tokens that are being generated. So instead, we're giving access to tools that all it has to do is generate the call over so that you're preserving a lot of tokens and the script can do a lot of the hard work. This will probably take maybe like 30, 40 seconds because there's a lot of different documents that are kind of uploading. While that's going, I can show you where they're being uploaded inside the console if you'd like to see.
Yeah, perfect.
I'm inside the Pinecone console and I can hit tool use podcast docs and I'll look inside my folder and you can see that we have all of our files kind of uploaded inside of our assistant here, which is really awesome. So that's great. Our assistant was made. Our documents are here. We can start querying over them and see what's what. Awesome. So we're here and now we can kind of ask this question that we're thinking about. So I pre-wrote the prompt because I find that it's always helpful to have that information kind of there so I can copy paste, especially when I'm doing live demos. So basically what this is going to say is, hey, what can you tell me about skill formation with AI? And how does that impact agent.md file creation? What I need to do is create an agent.md file and skill files that help users make better semantic search pipelines, especially ones that deal with sparse or multilingual data, which are the two embedding models that we two of the three embedding models that we support. So I'm going to say Pinecone, I'm going to say / Pinecone Assistant chat, and I'm going to say this query, and I'm going to hit enter. And you can see that whenever I'm using some of these / commands, there's options to kind of fill in the arguments, but I'm just going ahead and putting in my query and I'm letting Claude kind of figure out what information it should put in each field based on the context of the chat. And that's a really powerful way of using Claude Code because it has context to your previous conversation and your workspace and the data that we've kind of included with the Pinecone plugin. We can kind of let it figure out all of that sort of stuff. So we can see that I think we're getting a response back here. Oh yeah, this is super cool. So we're seeing this backward because I have to kind of scroll up, but I'll show you what the response is. So we can see the assistant response. Skill formation with AI and its implications can be understood through three aspects: the AI and skill development, role of structured context files. I'm gonna see if, yeah, right. So we have some information here to complement the agent.md file, create skill files that guide users in building semantic search pipelines, which can include tutorials on blah, 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 blah. And we get page level citations for this type of information as well. So if we were inside the console, we could actually click on these pages and we would be able to see inside the console, like where this information is getting pulled from. And so that's super cool. We were just able to do RAG with our documents, just like out of the box using Claude Code without having to write any code ourselves, like purely on the information that's kind of there. But that's the kind of benefit of making using the Pinecone plugin there. That's the extra thing I wanted to show you.
Yeah, very cool. It's making it so much more accessible and removing a lot of the questions I know I had that might have been intimidating me from getting into using vector databases. If I can just have a quick chat with Claude, fire it up, get some documents up there, seamless.
Exactly. And very often people could take this directly into production because you can interact with Pinecone Assistants via an API. So if you want to create your own web interface, you can just have it pipe into our Pinecone Assistant. Or maybe you're like, hey, I want a POC really quick. Like, I just want to know what it would be like to like implement an agentic search or like really simple RAG over my documents. Throw it into Assistant, see that it works really well, and then learn how to build it yourself using our plugin and the Pinecone vector database. So it's nice. It has a nice optionality, and it's also super fun for these kinds of demos. Like we can learn a lot about our data really quickly this way.
Absolutely. This was awesome. Arjun, really appreciate you coming on to teach us about vector databases and Pinecone. Before I let you go, is there anything you'd like the audience to know?
Hey, you can always find me on LinkedIn, or you can find me inside the Pinecone Discord. Just search my name, Arjun Patel, Pinecone. You'll probably find me. Feel free to shoot me a message or interact with me there, or inside our Pinecone Discord. It was awesome hanging out with you, Mike. This was so much fun.
Thank you for listening to my conversation with Arjun Patel. I really wanted to make sure that both you and I understood the need for vector databases in this point in time. They were all the rage before and kind of fell out of fashion, but there's still a lot of viable use cases for it. So I do hope you experiment with it, play around, try different chunking strategies, see how it works for you, because there might be a recommendation system that you didn't know you could build, which is enabled by this technology, or maybe just your little chatbot can get better performance if you get a little more meticulous in the way you structure it. I hope you enjoyed this conversation, and I'll see you next week.